Good morning, everybody. Hopefully you're having a good day and you're going to have a wonderful morning with your host, me, Dr. White. I still have some stuff up there. By the way, my best friend, who's about my age, is totally bald except here. I'm doing a lot better. All right. Let's do the lab first. And does everybody see the lab now? You see it on the screen? Thank you. I'm going to have a club called my Thumbs Up Club. But anyways, this is today's lab. You can download this from Blackboard. Today's lab deals with calories in a nut. Now, when you're talking about chemistry, an important aspect of chemistry is energy. Energy is something, various forms. One energy you can see, the light, is a form of energy, but the one form of energy most of you are familiar with are heat. You know, if you have a flame and put your hand over it, do not do that. It gets burned because of the heat from the flame. And when you cook your food, you're adding energy to cook your food in the form of heat. Whether you use electric or gas stove or oven, that's how you're cooking your food. Now, food has energy. All molecules, my shirt and everything, have energy. Now, how can you measure energy of certain things? By when it gives off or reacts with something and gives off heat. And you can measure that heat. And that's what you'll do today in today's lab from Dr. White. Have fun with the calorimeter with the octane in Zoom, not Zoom, in Labster. But again, one way of measuring heat is called calories, and I think you've all heard about that. As you know, different foods contain different amounts of calories, energy. In today's lab, you'll be measuring the calories in a nut. Have you noticed most of the really good, dangerous foods are all high calorie, like you shouldn't eat that much? Don't know why. You know, like good things like potato chips, French fries, salami, all the good stuff in life. But anyways, you'll be working with a nut. Now, quick Dr. White story. We've been doing a version of this lab for many, many years at the other college I teach at, and we do something similar at COD. And a number of years ago, there had been a number of stories in the news about how students were being affected and people were being affected who had allergy to nuts. And it was about 2 weeks or a week or two before we were going to do this lab in my class and other classes at ECC, Elgin Community College. I saw that and I asked my class, does anybody here have severe allergies to nuts? And 2 people raised their hands, which immediately I know we couldn't do that lab with nuts because you're burning it and some of the things from the nuts will get in the air and these people could be very badly affected. So I talked with the other faculty members. We tested some things. You know, it burns real good also, corn chips. And I don't think too many people are allergic to corn. And we've been doing at the other school corn chips, but because of the safety of the internet, I don't have to worry about you guys being affected by the nuts in this lab. True story. All right. Now, how do you measure the calories in a nut? Well, you react certain chemicals. The main calories are fats and oils in a nut, reacts with oxygen. We call this combustion. And this reaction gives off heat in the form of a flame, and the flame will heat a certain amount of water. And the difference in temperatures when you start and finish is called delta T and can be used to calculate the heat given off by the nut and thereby calculate the heat, what otherwise known as the calories in a nut. Now, what you use to capture the heat is called a calorimeter. Now, in the Labster video or simulation, I should use proper terminology, they've got a calorimeter that costs maybe $5,000, $10,000. For this lab, if you did it in COD or ECC, you'd use a pop can, which doesn't cost tens of thousands of dollars. And the difference in temperature of the water, delta T, along with what's called the heat capacity of water, how much energy it takes to raise the temperature of water 1 degree, to heat a gram 1 degree will allow you to calculate the calories in a nut. Now I have 2 videos here that I'd like you to watch, but let's look at one of them because I thought I'd bring up something interesting. Dr. White's getting good with Zoom.
I'm going to be conducting the calorimetry lab with a peanut. The first thing you need to do is read through your lab and then make sure that your setup looks like
Everybody
this.
see the video?
Make sure also that your
Thank you.
stick
Thanks to my
source
thumbs up,
is
people.
measured out as being only 3 centimeters away from the base of your can. So make sure to measure that. You're going to need 100 milliliters of water.
Now I'm going to skip this part because I want to show something.
Water in my can. Place your food source on fire. This because it does take some time to start the food source burning.
Not really, but I'll show you something.
Be very careful with matches.
Student, the hottest part of the flame is at the top of the flame. Notice she's trying to light it with the middle of the flame, and she's having, now she lowers the candle, a little more, a little more,
with the water in it, so that
a little more.
can be recorded.
When you do it in real life, if you know how to use a flame,
You'll start to hear some little kind of clicking when it starts to burn. That is a little indication to you, like kind of popping, that the food source is on fire.
Well, you can see the flame.
You're going to let that burn and heat up the water. Now that the peanut is completely burnt, you're going to check your ending temperature on your thermometer. For the data for the peanut, you're going to record a temperature of 33.5 degrees Celsius. You will be conducting this.
All right. Well, that's what you're going to be doing. Once again, I just thought I'd point out, by the way, Dr. White, when he was younger, was a closet pyromaniac. I love to burn things. Most good organic chemists, when they were young, did that. I've talked to many who I know, and we all have the same background. But if you have a candle, the hottest part of the flame is not in the base or middle. It's on top or about a ½ an inch above, which that student obviously didn't know because she probably wasn't an organic chemist and had pyrotechnic experience like Dr. White. Now, in the lab, what you will do is you would have built your pop can calorimeter, add 200 milliliters of water, which because the conversion is 0.200 kilograms. You'd measure the initial temperature. You'd put the nut on the holder, which is a trick to keep it balanced there, but it's doable, and I show students how to do it. You weigh the nut in the holder. You put the nut and holder under your pop can. You light it. And by the way, if you do it correctly, it lights almost immediately. The first time I was going to teach this lab, which I didn't do as an undergrad, I was warned by other faculty, warn your students, it really burns. And both the nut and what we do now, the corn chip, really are quite flammable or give off a lot of a large flame. It's amazing. And when the nut stops burning, you'll measure the temperature again of the water and the weight of your residue, nut residue, and holder. Now, be sure to properly dispose of your nut residue, we usually have a can for that or bottle that we then properly dispose of, not in the garbage. And the water goes down the drain and your pop can goes in the recycle bin. All right, now, what you see now, the data and calculations, you would do yourself. I'm giving you some of them. Here's the mass of the water. You need that. Here's your final temperature, your initial temperature. Your delta T is number 1 minus number 2. See how nice Dr. White is to really help you out? Now, your initial weight of your nut and holder was this. Your final weight was this. And the difference, 3 minus 4, was the weight of the nut consumed. You never burned a whole nut. But what you burn is what is responsible mainly for the calories of the nut. Now, you have to calculate the delta T right here. You also have to calculate the weight. Now, to find out the calculated calories in your nut, you use formula 1A, I mean, and that's this up here. You put in the mass of the water, 0.200 kilograms, your delta T, which you calculate, and the specific heat is 1.00. And you'll get a number here. Now, to get the actual calories per gram of the nut, you take this number 5 that you just calculated with formula A, and you divide it by formula C here, the weight of the nut. And then you'll get calories of the nut. And that's how you do it. And you can watch the video to see that. Now, here's some questions you need to answer. One thing, if we're doing it in class, usually we use planter's nuts, peanuts. And if you look on the label, when you do a little math, which I helped you out, the actual on the can is 5.71 calories per gram. And did you get similar? That's what I'm asking. And if you didn't, what would be possible errors for that? Now, if you remember, you have a flame under a can. Is your flame really close to the bottom of the can or not? That will affect it. Did you weigh the peanut correctly? Also, did it fall over before it went out, which theirs didn't? Those are all things that sometimes happen. So that's the lab. I would also ask you to look at the general chemistry thermodynamics Labster lab. Just log in, try it out for a little while. But the actual thing you have to do is what I just showed you. Fill out the data. If you don't have a printer, you can just write out the couple things you have to calculate and the answers to the questions on a sheet of paper, and follow the procedure on how to create a PDF and upload it to the assignment area. As per my syllabus, all labs are due the next lab period. So this lab is due this Thursday. In the summer, things go a little quicker, but I think you'll see it's pretty easy to do my labs. I don't ask for a 30-page write-up. That's a waste of time, and you don't want to waste all your time in your life on things that are wasteful. I don't. So, any questions about today's lab? Ones?
I do have a question.
All right, what's your question?
Can you explain, like, what exactly do we have to do with Labster? We just look around.
Say it again.
What exactly do we have to do with Labster?
Well, on Labster, all you got to do is take a look at the video or their simulation, try it out.
Okay, thanks.
And you don't even have to finish this one. Just be on there long enough to know that I can look, that you tried it out, and somebody from the department, did your people use Labster? Yeah, here, you can look at the fact they logged in. But do not get frustrated by it. I started to. Oh, by the way, at the end of Labster, they ask you, would you recommend this lab to someone else? And I put down 0. And then they asked for comments, and I won't put my comments on the air, but they were pretty, how should I say? But think on the bright side, by having Labster, you'll get credit for an actual lab course, which will help you to whatever degree program you are. All right.
Hi, Dr. White, I have a question.
What
So for the calories of the night,
you're breaking up.
do the measurement on the Labster?
No, first of all, your audio is breaking up. In Labster for today's lab, all you got to do is log in, try the simulation. Try the simulation, and then I guess she logged out for a second, having trouble with her connection. I'll say this again. For Labster this semester, just log in, try as much as you want, and then log in. Don't worry about that, any kind of stuff, and that way it will work, okay?
Okay, so we don't have to do all the experiments on the Labster.
Well, try them all, but you don't have to finish them all.
Okay, there is options. There are a lot of options over there because I was checking yesterday and I finished the acid and the bases.
All right, listen carefully. Look at my syllabus. Hold on. Through the miracle of modern computers, give me a second. This is in the syllabus, the schedule. So for today, all you have to do is, if you look at the general chemistry, there's one called something chemistry thermodynamics. Just open it up, take a look at it, try it for a couple minutes and close it. For Thursday, there's one called periodic table of elements. And all you have to do is go and open it up, try it a little. Don't forget to put your safety goggles and glasses on. Oh, anyways, that's a waste of time for that lab. But anyways, and just try a little of it. On Tuesday, good news, that's one of my handouts. Then the ionic covalent, I got to look at. I got to look at this one too. And I may create some of my own handouts. And this one will be my own. Does that help? If you're not sure, email me, or let's see, today's Tuesday, tomorrow, Wednesday, come to my office hour and I'll be more than happy to help you out. All right, Nikki, I just saw your post. What you just have to do at Labster is log in, try them, and I can see you logged in and you'll get credit. Unless I have like today's lab, you have to do my handout. And that's really what I'm going to use to determine your 11 points maximum for the lab today. Does that help, Nikki? You're welcome. All right. Let's move on to problem set number 4. And one of your colleagues found a mistake from Dr. White. And I'll show you where it is so you can correct it. All right, let's go through chapter 4, practice problems. If you have any questions, just speak and I'll hear you, because when I have this in sharing mode, I don't see the chat that easily. All right, first question you should know how to do for test number 1, which is this Thursday when I'll be allowing you to download it. You'll have all day to finish it. And you shouldn't need that much time, but because some of you have different schedules or something happens to your computer or internet connection, that's why I give extra time. All right, how many atoms are each of the following molecules? Well, you have to know your chemical symbols: HCl, 1 hydrogen, 1 chloride, 2. Now, when you have a number to the right subscript of the element, that tells you how many atoms. So in sodium sulfate, which I think I did yesterday, you have 2 sodium, 1 sulfur, and 4 oxygen. That's 7. Now, when you have a bracket, you multiply the number of atoms inside the bracket times the number to the right subscript of the bracket. So in this case, you have 1 magnesium. Now, 1 hydrogen times 2 hydrogen. 1 carbon times 2 outside the bracket, 2 carbon. 3 oxygen inside, don't forget that number, times 2 is 6. That adds up to 11. Now, where I made my mistake, and you can see me hiding my face with my hand, this should be not 7, that should be 9. So change that to 9. That was my mistake, because 1 calcium, 2 nitrogen, 3 times 2 is 6. My first grade teacher would be very upset with me now. All right, let's continue. Something you really, really should know. What are the 3 subatomic particles of an atom? And they are the electron, proton, and neutron. Again, electron, proton, neutron. Now, what charge is on a proton? It's got a positive charge. What charge is on an electron? It has a negative charge. And you should know 3 subatomic particles: electron, proton, neutron. And proton, positive charge; electron, negative charge. I think it's on the next page. Neutron, no charge. I guess I didn't have one like that. All right, now, how many electrons and protons do each of the elements have? 1 point each. Well, carbon, first of all, you have to know the chemical symbol, carbon. Hold on while I open up a periodic table. And you all should see the periodic table here. Let me check my thumbs up, people. You see the periodic table? Thank you, thumbs up, people. I'll call you TUP. Nah, I don't like that. Carbon. How many electrons and protons? The number on top here, the atomic number tells you the number of protons, number of electrons, 6. Let's go back and do one more. And if we do gold, if you looked up the atomic, know the atomic symbol, AU, you'd see the atomic number is 79. So there's 79 electrons, 79 protons. So if you know if you know the number of protons in a element, you also know its atomic number. And let's do one more. Oh, bromine, I like that. 35 and 35. Br is the chemical symbol for bromine. And that's how you do it. And finally, I'm asking you, give the name of a halogen, it's the chemical symbol. Give the name of an alkali earth, inert gas, and alkali metal. And if we go to the periodic table, the first column, not including hydrogen, are the alkali metals. So an example of an alkali metal, lithium, sodium, or potassium. The second column are the alkaline earth metals, and those are magnesium and calcium are the two I asked you. You could put down strontium, which I like because it makes fireworks red, but the only two I asked you to learn here were magnesium and calcium. Now, where are the halogens? The halogens are the second to last on the right column. And you could put down fluorine, chlorine, bromine, or iodine are the ones I asked you. And finally, the very last column on the right, as you're facing your monitor, tea break. But anyways, as you're facing your monitor, this column is the inert gases, and helium, neon, argon, krypton, xenon are examples you could all use. And the last one, give an example of an element that's a metal: gold, silver, iron, lead. Those are all examples. Platinum, palladium, you could have put down. And that's problem set 4. Any questions on any of the material in chapter 4?
Yeah, I do have a question. On the problem set, it said inert gas. That's halogens, right?
The what?
It said inert gas.
Yep.
Those are the halogens?
No, inert gas would be, do I have a halogen down for an inert gas?
No, I'm asking just about the question.
All right. The type of question, let's go back to that. Give the name and chemical symbol for each of these. So a halogen would be the second to the right column of the periodic table. Alkaline metal would be the second to the left. Inert gas would be all the way to the right. And finally, sodium, which is alkali metal, all the way. Let's do this. Hold on. One of these days, I have to email whoever created this and thank that person. Yes, my thumbs up, people. Everybody see the colorful periodic table? Thank you, thumbs up, people. All right. Now, this column in, I guess it's sort of orange, is the alkali metals. You can see right over here. Here are your alkaline earth metals. Did I put inert gas? Yep. Now I see your question. I use the old name. That should be noble gases. Okay?
Okay, thanks. That makes sense.
Sometimes I don't make sense. Sometimes I don't even make dollars. Uh-oh, it's real bad humor Tuesday. But on a test, one, I'll make sure I use the right one, noble gas. Until about 1995, 1998, which is not that long ago. Yeah, it's not that short, but in my mind in life, it's not that long ago. We used to call that last column the inert gas, and I still do. So By the way, when you take the test, I will be checking about every half hour or so my email throughout today, or maybe every hour. So if you have a question while you're taking a test, like if I did something stupid like that, bad doctor would be nice. But anyways, email me and I'll send out a correction to everybody. But usually I do that. Yep. I use the old name. On test, I'll use noble gas. I still like inert gas, but somebody made it react, so it's no longer can be called inert gases. All right. Well, in that case, let's move on. Now, I had been talking yesterday briefly about the polyatomic ions. These are ions that exist as a single unit. They have a negative charge. Where I have know these names, I'm not going to ask anymore. I used to, but I won't, because I've sort of cut back on naming, otherwise nomenclature. I'll give you some names of things, but when we do it in class, but to actually ask on a test, what's NaNO3 sodium nitrate or nitrite, I'm not going to do that. So we've done chapter 5, and it's time for chapter 10. We're moving along quickly, but there's a lot to do these chapters. Remember, this material is for test 2, not test 1. All right, let's continue on with chemical bonding. And remember, there are 2 types of bonds. One is ionic, which is the transfer of 1 or more electrons from one atom or group of atoms to another group, atom or group of atom. I'll be adding some extra stuff that isn't in the book. Oh, that reminds me. Let me get you all up here. Everybody, how many of you are not reading the book or didn't buy it? Give me a thumbs up. And either on your screen or what. I see a lot of you are. Aren't you glad I just saved you $120? And you'll find Dr. White does a good job. All right, I just wanted to check. All right, let's get back to chapter 10. Now, you should also know, and I discussed this already, but I'll discuss it again. And let me just do a quick check with my thumbs up, people. You see covalent bond on the screen? Thank you. All right, a covalent bond results from the sharing of 1 or more pairs of electrons between atoms. Now, ionic, you're transferring 1 or more electrons from one atom or a group of atoms to another atom or group of atoms. Where covalent, you're sharing 1 or more pair of electrons. If we were in class, I don't know when I started doing this teaching, but whenever I say covalent bond, I always do this. You're sharing pairs of electrons, holding hands, sharing them, locking things together. Whenever I say covalent bond, I do this. I'm in a classroom. Now you're getting a full Dr. White classroom experience. Now, an important aspect of understanding chemical bonds are valence electrons, which we talked about briefly, and something called electron dot symbols. Now, what is this? It's a convenient way to represent the valence electrons. What are the valence electrons? Well, those are the outermost electrons. Those are the electrons that are involved in chemical reactions. And that's the fun part of chemistry. Now, your book and a lot of books call them electron dot symbols. No, they really should be called Lewis structures in honor of Dr. Lewis, who just invented them. And I like to, and most chemists like to, honor people who have done great things by attaching their name to it. Well, on a test, I will use the term Lewis structure. Now, just a reminder, valence electrons are representative element, are the same for all elements in the column, and the valence electrons are determined by the Roman numeral or the numeric Arabic number on top of the column. And the maximum valence electrons any element can have is 8. 1 to 8, never less than 1, never more than 8. Now, how do you do a Lewis structure? Lewis structure consists of an element symbol and one dot for each valence electron. Turns out, which is why I'm not asking you to learn it, valence electrons are never d or f orbitals or subshells. And here's the important thing. Place one electron on each side of an element symbol before putting a second electron, valence electron on the side. So you put one on each side of the element symbol, 4 sides, before you start doubling up. Oh, look, it's Lewis practice time. Let's have some fun. Hang in there. All right, first question would be, get my pad over. All right, so if I were to ask on test, draw the Lewis structure for 3 points each, A, sodium, the first thing you have to know is how many valence electrons sodium has. Remember, Lewis structures deal with valence electrons. So what we need to do is go to the periodic table. And since I've been running around, let me just check. Everybody see the periodic table? Thank you. Thumbs up, people. And you have to know sodium is Na. You look at the top and you see the number 1. I also put it on here in red, so it would be obvious. And hopefully you're not red colorblind. If anybody's colorblind, let me know if you're having trouble with this table on a serious note. Sodium has 1 valence electron. So now we go back here, and how do you draw the Lewis structure? You draw the chemical symbol and you put a dot. Now, which side can you put the dot? Any side. This is one way. It would be just as correct to put it here or here or here. Oh, let's do another one. And the question would be, draw the Lewis structure for oxygen. Well, first of all, hopefully you've learned the chemical symbol for, that's awful looking oxygen. But anyways, chemical symbol for oxygen is O. And now you need to go back to your periodic table and find oxygen. And it's right over here. And then you look at the top of the column. If you know your Roman numerals, VI is 6. But for those who are never taught that in school, I put the regular number 6. So oxygen has 6 valence electrons. Now, remember, you put 1 dot on each side. That's 4. Remember, oxygen has 6 valence electrons. And now you double up. Now, organic chemists, don't ask me why, but this is how I learned it. And good habits, Dr. White doesn't change. Puts the next dot, that's 5, and the last dot here. Now, it would have been perfectly correct. Now I got to force myself to do something unnatural to me. To do that, all you had to do is 2 sides have 1 dot and 2 sides have 2 dots. What would be wrong because notice you have 3 dots on a side. You can never have more than 2. And you put 1 dot on one side before you double up. And that's the Lewis structure for oxygen. Now, I have to share with you people. So let's do C. Why don't you do the Lewis structure for chlorine? And hold on, here's your periodic table. Have fun. Draw the Lewis structure for chlorine. I'll give you 8.7 seconds more. 8, 8.1, 8.3, 8.5. Time's up. Notice chlorine has 7 valence electrons. The number at the top of the column tells you how many valence electrons. And how do you draw the Lewis structure? You draw the chemical symbol. Ooh, not bad for this tablet. Then I have 7 valence electrons. You don't have to put this down in the test, but I like to put it down because it reminds me how many dots I have to do. I'll do 1, 2, 3, 4. I have 3 more. 5, 6, 7. This is one way. You could have easily done it this way. And the Lewis structure, there are 2 more I could draw. 3 sides have 2 dots. 1 side has 1. Oh, let's do 1 more. These are real fun and easy. What would be draw the Lewis structure for argon? For those who haven't, hopefully you have, argon chemical symbol is AR. Have fun. 10-second warning. Nine 9.1, 9.3, 9.75, 10. Time's up. Oh, why did I leave that? Let's go back here. Argon, AR, how many valence electrons? You look at the top, and the answer is 8 valence electrons. And now we'll go back to our place where we're writing. So I have 8 valence electrons. You don't have to write this, I do. Chemical symbol AR, 1, 2, 3, 4, 5, 6, 7, 8. So the Lewis structure for argon is 8 valence electrons, and each side has 2. This is all one big, this is an ugly dot. Sorry about that. But anyways, each side has 2 dots. And see how easy chemistry is? It's not that bad. And it's even fun. If I say that enough times, you'll believe me. And we did some of these. I didn't do magnesium, but you can try that on your own. All right, now there's something I'm turning the switch off for next 2 slides. Click. Will I ever ask on a test what's the octet rule? No, but you should be familiar with it, which is why. Now, the octet rule is in both ionic and covalent compounds, atoms tend to acquire electron configuration of the nearest noble gas. Well, I got it right there. I didn't call it inert gas. And that means atoms want to have 8 valence electrons because that makes them very stable and very happy. I bet you didn't know atoms like to be happy. They do. And remember, valence electrons, certain arrangements are most stable when you have 8 valence electrons, which means they don't automatically change into something else. Hold on. Got rid of that quickly. Sorry about that. And the most stable arrangement is 2s and 6p, and n can be 2, 3, 4, whatever. This is the shell number, this is a subshell. In other words, what it's really saying is 8 valence electrons, which all noble gases have. And the octet rule is in compound formation, when you're making molecules, atoms of elements lose, gain, or share electrons in such a way that their electron configuration becomes identical to that of the noble gas nearest to them in the periodic table. Oh, look, I got fancy with colors. And that means they want 8 valence electrons. This I'll never ask you on a test, but it's very important. Now, certain elements can form what we call positive ions. In ionic bonding, you have the transfer of electrons from one atom to other. And when an element loses 1 or more electrons, an ion with a positive charge is formed. By the way, switch is on now, and we call that a cation. When you lose electrons, you get a positive charge. Now, question is, what charge what ion does magnesium form? So let's look at how do you do this. Now, magnesium, I would have written magnesium, not the chemical symbol. You have to look at the periodic table. So let's go to periodic table. And here's magnesium. Now, what is the closest noble gas? Usually I say inert, but Dr. White was a good boy today. What is the closest noble gas numerically to the atomic number? You have three choices. Neon at 10, argon at 18, and really it's only two. You could say krypton at 36. Now notice the difference between the atomic numbers of neon at 10 and magnesium is 12. Can everybody see the? Okay. Anyways, neon is 10. Magnesium is 12, so that's two different. Magnesium to argon, 12 to 18, is 6 different, which is a smaller number, 2. So magnesium wants to go from 12 electrons to 10 electrons. Let's take a look at how we use that. And if we were in the classroom, you'd see the periodic table on the board while I'm doing this, but we're not, so I got to switch back.
Can you explain how you'd found that again?
Of course. Here's magnesium. You want to find the nearest noble gas that's closest to it numerically based on atomic number. You want to find the nearest noble gas that's based on atomic number. In other words, which one has the smallest difference between 12? You have two choices, 10 neon, 18 argon, AR. What's the difference between 12 and 10? 2. What's the difference between 12 and argon 18? 6. Which is the smallest number? And hopefully I'll pick 2. And therefore, that's why you pick neon. It wants to have 10 electrons, the same number of electrons as the nearest noble gas, because that makes it stable. Did that help? All right, so now what do we know? We know, there we go. This has 12 electrons, 12 protons. Magnesium wants to go to 10 electrons, because that's how many the nearest noble gas has, but it never loses protons. Now, each electron has a minus charge. Each proton has a +1 charge. Do the math. This is -10. This is +12. And if I add them together, I'll get a +2. And this shows you the charge, but it asks what ion does it form? And you show the ion by the chemical symbol, and then superscript to the right, you put the charge. Now, there are two ways to doing the charge. This is the old way, which Dr. White still likes. Other people are also in your book, if you had one, would do this. Which is right? On my test, either one, because I'm the one grading it. And that's how you determine a charge. Now, what would be the answer you would have to write for this question? Either one of these. This stuff right here, I'm just showing you how you do the thought process. Do you have to write this on a test? No, but if you want to, it makes your life easier, go right ahead. And if I look at the clock, I'm just about out of time. All right, listen up. Remember, the lab that you did last Thursday, the density lab is due today. Don't hand it in late. You got until I think the end of the day to get it in, upload it to the assignment area of Blackboard. Don't forget the Calorie of the Nut lab today. Just go into Labster, just look around and then log out. And then do the download for the lab, and that's due Thursday. Don't forget, Thursday will be test number 1. And with that, I haven't done it all day. With that, goodbye, gehen gesund, be healthy. And I'll see you tomorrow.